Okay, so section 7.2, we're going to do hypothesis testing for the mean. For the mean when sigma is known. Okay, so when I know sigma, this is the hypothesis test we're going to run through. Okay, recall from last time, a decision rule based on the p-value. What did we say? If the p is low, the null must go. Okay, if the p is low, the null must go. The decision rule says if p is less than or equal to alpha, so if the p is lower than alpha, reject H naught, reject the hoe. Okay, if the p is low, reject the hoe. All right. If the p is bigger than alpha, fail to reject the null. Fail to reject the hoe. Okay. So we've got a problem. I'm given a p-value. The p-value is 0.0256, so about 2.5% or a little bit more. What is your decision given a level of significance? Remember, if you see level of significance, think alpha. Okay. Now, we're told for this first one, alpha is 0.10. All right. The p-value that we calculated, so let me draw you a picture here, give you an idea. I'm just going to assume it's, without loss of generality, I'm going to assume it's a right-tailed test. Okay. So we're given some alpha cutoff point. So this is my alpha cutoff point. Any p-value that's smaller than alpha, that area over here is smaller than alpha. Okay. I will say the p is low, the null must go. If this is the null hypothesis, this distribution, and I find a p-value that's like way out here, what does that mean? That means that it's likely that the hoe is lying. Okay? So if the hoe's lying, we reject the hoe. Okay? So small p-value, that's implying that it's not likely that it came from this hoe distribution here. Okay? So for this one, this first one here, I had an alpha 0.10, a p-value 0.0256. It looks like the p is less than or equal to alpha. 2.5% smaller than 10%. So what do? My decision, reject the hoe. The next one, if alpha is 0.05 and p is still 0.0256, guess what? P is still lower than alpha. Okay, so we are still on this side over here. All right, we're even smaller. Okay, so we're even smaller, so maybe this is my new alpha, 0.05, versus that first alpha that was 0.10. Okay, now I'm just more sure that the hoe is lying, so I'm going to reject the hoe again. Okay. Oh, I'm sorry. I've done this wrong. Okay, back up. Let me reverse what I just said here with this little picture. Okay. Now, it is true that p is less than alpha. 2.5% is smaller than 5%. However, it's alpha that is changing for us. Okay, so the p-value is staying at this 0.0256 in this picture here. Originally, we had an alpha equal to 0.10, okay? But what happened was when I reduced my alpha to 0.05, that made it go closer here. So we lost this little bit of area that I had shaded in here. Okay, so now this is my new alpha 0.05. But we're still in the rejection region. Okay, so reject the host still. This last one though, this is where it changes. Alpha 0.01, P is still 0.0256. Guess what? Now the P value is greater than alpha. If you have a large P, we fail to reject. Fail to reject the hoe. Okay? Why do I fail to reject the hoe? When I look at this in a picture, okay, my P value, so here's my alpha, right? Here's my alpha 0.01. My P value is greater than the alpha value, so that means that P is over here. The P value, okay? So if the hoe is this thing right here, that distribution, and my cutoff point is everything to the right over here. Anything over here, it's like, man, that hoe's lying, right? But if I'm over here in this region, it looks like, well, maybe the hoe's lying, but maybe the hoe's not lying. So I fail to reject. Okay, I fail to reject now because I'm not in the rejection region there. All right, so that's based off of P value. If the P is low, the null must go. That's the key to remember. Find the P value for a left-tailed test. Okay, so P value for a left-tailed test. What do we need to do first? First, I need to draw a picture. Now, what does a left-tailed test tell me? All that tells me is whenever I draw my line, I shade to the left. That's all it tells me. They give me z equals negative 2.23. What's always in the middle? 0. So what side of 0 are we on? We're on the negative side, so we're over here at negative 2.23. That's my z value, okay? So this is my z value. So I want to know the P value. The P value, if you'll remember the definition for P value, it's the probability of finding a statistic as extreme or more extreme. So as extreme or even further extreme from this assumed mean, right? So what is that? That's the shaded area right here. How do we find that? We go look it up in the chart. Okay, I go look it up in the chart. So let's see if I can go to my table. Standard normal, negative 2.23. So negative 2.2 and negative, and then the 3. So right here, 0.0129. 0.0129. Okay? All right. Let's go back. So this area, the P value, is 0.0129. 0.0129. Now, if P equals 0.0129 and alpha is equal to 0.01, okay, what does that tell me? That tells me that my P is larger than alpha. With a big P, what do? I fail to reject. You only reject a little p, all right? So big P fail to reject the null hypothesis, HO, okay? All right. Next up, instead of a left-tailed test, we're going to do a two-tailed test, okay? The only difference between a left tail and a right tail, if it had been right, we would have shaded this way. And how would you find that probability? You would take that value and do 1 minus that value to get the right side, okay? So that's how you would do right-tailed test. For a two-tailed test, find the p-value for a two-tailed with z equal to 0.214. Okay, two-tailed test, what's in the middle? 0 is always in the middle. Z over here at 2.14. Okay, what do we know about a two-tailed test? With a two-tailed test, okay, with a two-tailed test, we have a tail on this side, but we have a tail on the other side. If Z in the middle is 0, and I have 2.14 on the right side, then I have negative 2.14 on the left side, okay? So a two-tailed test says that I need to shade on the right and the left. So that's a two-tailed test, okay? But do I put all of my p-value on one side? No. I put half of my p-value over here and half of my p-value over here, okay? Now, a z-score of 2.14, if I go look it up in the chart, 2.14, that's going to give me 0.9838. Is it possible to have 0.9838 in this little tail here? No, it's not. Remember, the z-score tells you what? Area to the left, cumulative area. So that's all this area right in here. Do I want all that area? No, I want the complement of that area. So what do I have to do? I got to do 1 minus 0.9838. And when I do this, I'm going to get 0.0162. Okay, 0.0162. Now, if 0.0162 is on this side, what do we know? What do we know? 0.0162 is also on that side. So what is my p-value? My p-value for a two-tailed test is 2 times that one tail. Okay, so all I'm doing is doubling it up. I have it over here on the right. I got it here on the left. I got to count it twice. So I multiply by 2. And I get 0.0324. 0.0324. Now, if my total p-value is equal to 0.0324, and I have an alpha equal to 0.05, then my p is less than alpha. If the p is low, the null must go. So what's that tell me? Reject the hoe. Small p, reject the hoe. Okay? That's my decision. So the two-tailed test is a little bit trickier, but if you draw the picture, you will see why you have to double it. Okay? With a left or right-tailed test, you find it, and you don't have to worry about doubling because all the area is in the left tail. Or if it's a right-tailed test, vice versa, all the area will be in the right tail. Okay. So, z-test. The z-test for a mean, mu. Very important here. The z-test for a mean mu. This is the hypothesis testing for the mean when I know sigma. So a statistical test for the population mean mu. Okay? The population mean is mu. Now, the test statistic, if it asks you to calculate the test statistic, all right, the test statistic is x bar, the sample mean. All right, sample mean. You guys know how to get the sample mean by now. The standardized test statistic, that's going to be the next thing. How do we standardize something? To standardize, what do? We take the value minus the mean over the standard deviation, right? So what is it? It's x bar minus the mean over the standard deviation divided by the square root of n. This is the central limit theorem. With the central limit theorem, 1, you have to have a random sample. Okay? But the second thing that has to be true, your population is normally distributed, or we have n greater than or equal to 30. So if you have 30 or more that you've gone out and sampled, or you know that the distribution is normal to start with, then you can use this z-test for the mean. Only then, your keys to the Ferrari, which every problem you're going to work in here is going to be a random sample, so that's given to you for free. But what you got to check is it normally distributed, or is n greater than or equal to 30? If it's not, then you can't work the problem. Okay, so some of the problems in your homework, that's how it's going to be. It's not going to satisfy until you just can't do the problem. All right. So what I want to do here is I want to go into some of the theory, and I'll come back and I'll work these examples in another video, okay? So we'll come back to those. All right. So here's continuing the video down more in the lesson part of things. Instead of a p-value to make our decision, okay, we can use the rejection region. Okay, this is the critical region of the sampling distribution. This is the range of values for which the null hypothesis is not probable. Okay, so if a z-score, a standardized test statistic, falls into this range, okay, then the null hypothesis, I'm going to say HO, is rejected. Okay? The null hypothesis, that's the null hypothesis. All right? A critical value, Z sub naught, so Z naught or Z sub 0, separates the region, the rejection region, from the non-rejection region. Okay? So let me try to illustrate what's going on here in a picture. Picture is a pretty good deal. So I'm going to do a right-tailed test since I did a left-tailed just a little bit ago. So with a right-tailed test, all right, I've got a z-score that falls in the range. I reject the hoe. That range, this is the critical value. So say I have some critical value right here, z naught. Okay? So z naught is determined by what we set alpha to be. Remember, alpha is the probability that we reject the hoe when we shouldn't. Okay? So we reject the hoe when we shouldn't. So what does that mean? All right, that means the hoe was true. Okay, so this red area here, this area is alpha. It's the level of significance. Okay, if we try to make it smaller, what we would do if we made it smaller, we would move it further to the right. And the further to the right, the more beyond reasonable doubt we are sure that the hoe's lying. But here it looks like that picture's, that alpha's pretty large, substantially large. Okay, if I run the test and I get some score over here, maybe I get an X bar over here or whatever, So a standardized test statistic. So maybe whenever I do that, I get some z over here. All right? If I get a z over here, everything over here is in the rejection region. So instead of looking at a p-value, we're actually comparing z-scores. So any z-score on this side, I reject the hoe, okay? But over here, if I get a z-score over here on this side, so I get some z-score over here, I fail to reject the hoe. What is this known as? This is the non-rejection region, okay? So that critical value, z sub naught, separates the rejection region from the non-rejection region. Okay, so everything over here is the non-rejection region, right? So the test says if z is less than z naught, then fail to reject the hoe. However, if z is greater than z naught, then reject the hoe. Okay? So if we're on this side of z naught, we reject. And if we're on this side of z naught, we fail to reject. Okay? All right, let me make this a little bit smaller so that I have more room to work with. Come on now. Okay. So, what's going on here? We've got normal distribution, two-tailed. Two-tailed. Sounds like my son is not very happy. Two-tailed test. Okay. With a two-tailed test, we have critical values on both sides. Z naught on the positive side, what's in the middle, 0. So on the left side, this is the negative Z naught, the other critical value. Okay, alpha now is split up. Alpha now is split up between two tails. Okay, so half my alpha is over here, and half my alpha is over here. That's my area. So my area equals half of alpha. Okay? This is all assuming that the hoe is true, right? The hoe is true. Now, the rejection region here, okay? So say I get say I get some z-score in here. So maybe I get a z between these two. If z is between the positive z and the negative z naught, okay, so what does that mean? That's somewhere in between here and here, okay? What do? We fail to reject. This is the non-rejection region, okay? So we fail to reject the hoe, okay? However, if z is over here, okay? So I find a z that's what compared with this negative z? A z that is less than negative z naught, okay? This is negative z naught. So if it's smaller than that, or if I get a z that is what? Bigger than positive z naught, then what do? Then I reject the hoe. I'm in the rejection region. Rejection region. I'm just going to copy and paste this, okay? So rejection region here and rejection region over there, okay? So hopefully that makes sense to you, all right? So as soon as they ask me, they're like, well, what happens if I get exactly what the critical value is? Well, guess what? That's not going to happen in any of our problems, okay? And truly, that would be a judgment call if it happened in real life. It depends on what you set your alpha to be. If you made like a really small alpha and you hit alpha right on the head, which is almost impossible to do, I'd probably say, yeah, there's probably enough information to reject it, okay? So it's really more of a judgment call there, but your problems, you're going to be clearly in one region or the other region. It's not going to be right on the critical value, okay? Because that's what separates the two regions. Okay, guys, I'm going to start a new video to work out those 3 examples.